This is lecture number 11 of the series of lectures entitled Bracket Algebra. First, the essentials of the previous lecture 10. We discussed Cauchy-Schwarz relation, the statement of which is inner product bra A ket B is less than or equal to under root norm A into norm B. Rewriting the expression of norm explicitly, we can restate it as inner product of bra A ket B is less than or equal to under root bra A ket A into bra B ket B. Also, we showed that if ket A, ket B are linearly dependent, then the equality sign holds. In other words, we have Now let us discuss Graham-Schmidt orthonormalization. We can orthonormalize a set of kets, that is, make them orthogonal plus normalized. We discuss first with respect to vectors. Consider a 2D plane, say the xy plane. This is origin O. This arrow is the x-axis. This is x hat and this is y hat. Consider two vectors, vector OL and it is this one, say. So this is OL vector equal to magnitude OL into x cap. Another vector is vector OP and it is this one, OP vector. Obviously, the two vectors we have considered are oblique to each other, that is not orthogonal. From this set, that is vector OL and vector OP, we will build two orthonormalized vectors. Let us start the process. Normalize vector OL, divide by magnitude to get vector OL by mod of vector OL equal to, for vector OL we write OL into x hat divided by OL. We get x cap, which is a unit vector, that is mod x hat is 1, modulus or length is unity. This is x hat, the normalized version of vector OL. And this was vector OP. Drop perpendicular from P on x hat and it is PP prime. The foot of perpendicular is P prime. This OP prime is the projection of vector OP equal to vector OP prime. Projection of vector OP along x cap equal to vector OP prime equal to OP prime into x hat. This can be written as vector OP dot x hat and this projection or scalar part is along x hat. So this part of the vector OP is along x hat and in other words it depends on x hat, linearly dependent on x hat. This part of vector OP is evidently not orthogonal to x hat as it is along x hat. Then what will be the linearly independent or the orthogonal part? The linearly independent part or the orthogonal part will be the full part, that is vector OP minus the linearly dependent part on x hat, which is vector OP prime. So the part of vector OP that is linearly independent or orthogonal to x hat is vector OP minus vector OP prime. Now this is OX, this is OP and the perpendicular projection gives PP prime. This is vector OP, this is vector OP prime, this is x cap and this is P prime P. So we can apply triangle law of vector addition to this right angle triangle OPP prime to get vector OP equal to vector OP prime plus vector P prime P. So vector OP minus vector OP prime is vector P prime P, which is P prime P into y hat. This is y hat since this is y axis. We have constructed the linearly independent part of vector OP that is orthogonal to x hat, and it is vector P prime P equal to P prime P into y hat. Normalize vector P prime P. Vector P prime P by modulus vector P prime P equal to P prime P into y hat divided by P prime P, and this is equal to y hat, which is a unit vector, that is mod y hat equal to 1, and it is orthogonal to x hat as x hat dot y hat equal to 0. Starting from vector OL, vector OP, this is vector OL and this is vector OP, we have constructed x hat, y hat. This is x hat and this is y hat. This set is not orthonormalized. This set is orthonormalized. We now rediscuss with kets. Consider a set of kets, ket psi 1, ket psi 2, ket psi 3, etc. This set is not orthonormalized. That is, inner product bra psi I ket psi j is not equal to Kronecker delta ij. Let us build orthonormalized kets. We label them as ket phi 1, ket phi 2, ket phi 3, etc. We shall build this set from ket psi 1, ket psi 2, ket psi 3, etc., which are not orthonormalized. And we shall make this set of ket phi's satisfy the orthonormalization relation bra phi m ket phi n equal to Kronecker delta mn. Let us start with ket psi 1. The norm of ket psi 1 is under root bra psi 1 ket psi 1 is not equal to 1. Normalize ket psi 1, divide by norm of ket psi 1. This ket is say phi 1. Let us call it so. Check it. Norm of ket phi 1 is, we use ket phi 1, and from here bra phi 1 is, so the norm of ket phi 1 is this is equal to 1. So ket phi 1 is derived from ket psi 1, where ket phi 1 is normalized, though ket psi 1 is not normalized. Consider another ket psi 2. Projection of ket psi 2 on ket phi 1 is the inner product bra phi 1 ket psi 2, which is the scalar part. This into ket phi 1, which is the direction part. Now this part is scalar and can be placed anywhere, and hence let us place it here. So we write ket phi 1, which is the direction part, and then the scalar part bra phi 1 ket psi 2. Let us note the importance of this part, ket phi 1 bra phi 1, which is an operator. We shall show this in the next video, that projects out ket phi 1 from ket psi 2. This portion is a part of ket psi 2 that is linearly dependent on ket phi 1 and is along ket phi 1. The part of ket psi 2 that is linearly independent of ket phi 1 and so orthogonal to ket phi 1 is the remaining part, which is ket psi 2, which is the full part, minus the linearly dependent part. Let us call it ket chi. Say, we normalize ket chi. Ket chi by norm of ket chi. Let us write the expression of ket chi divided by norm of ket chi. Let this be ket phi 2. Call it. We thus have obtained two kets, ket phi 1, ket phi 2. Check orthogonality. Consider the inner product bra phi 1 ket phi 2. This is equal to bra phi 1, and let us put the expression for ket phi 2. Since ket phi 1 is normalized, the inner product is 1. So this is 0. This implies that ket phi 1 and ket phi 2 are orthogonal. Check normalization of ket phi 2. Let us find norm of ket phi 2. Ket phi 2 is, and bra phi 2 is, hence the norm of ket phi 2 is 1. So ket phi 2 is normalized. So far we have got two kets, ket phi 1, ket phi 2, which are orthonormalized. That is, this set has been derived from the two kets we started with, that is ket psi 1, ket psi 2. These kets are not orthonormalized, that is, consider another ket psi 3. Projection of ket psi 3 on ket phi 1 is the inner product bra phi 1 ket psi 3 into ket phi 1, where this is the scalar part and this is the direction part. Again, this being a scalar, it can be placed anywhere, and let us place it here. This gives ket phi 1 into the inner product of bra phi 1 ket psi 3. This portion is in fact an operator. We will show it in the next video. It projects out ket phi 1 from ket psi 3. Projection of ket psi 3 on ket phi 2 is the inner product bra phi 2 ket psi 3 into ket phi 2, where this is the scalar part and this is the direction part. Again, this being a scalar, it can be placed anywhere, and let us place it here. This gives ket phi 2 into the inner product of bra phi 2 ket psi 3. This portion is in fact an operator. We will show it in the next video. It projects out ket phi 2 from ket psi 3. The part of ket psi 3 that is linearly independent of ket phi 1 and ket phi 2, and so are orthogonal to ket phi 1 ket phi 2. Ket psi 3, the full part, minus the linearly dependent part along ket phi 1 and ket phi 2. Let this be ket psi. Call it so. Normalize ket psi. Ket psi divided by norm of ket psi. Put the value of ket psi divided by norm of ket psi. Let it be ket phi 3. Call it so. We have obtained three kets, ket phi 1, ket phi 2, ket phi 3. Check orthogonality of ket phi 3 to ket phi 1 and ket phi 2. Consider the inner product bra phi 1 ket phi 3. Putting expression for ket phi 3, we get and since ket phi 1 is normalized, this is 1. Since phi 1 and phi 2 are orthogonal, this is 0. This is 0, meaning that phi 1 and phi 3 are orthogonal. Consider the inner product of bra phi 2 ket phi 3. Putting expression for ket phi 3, we get as phi 2 and phi 1 are orthogonal, this is 0. As phi 2 is normalized, this is 1. So the answer is 0, meaning that phi 2 and phi 3 are orthogonal. Hence ket phi 1, ket phi 2, ket phi 3 are orthogonal. Check norm of ket phi 3. Putting expression of ket phi 3 and bra phi 3, we have norm of ket phi 3 is 1. So ket phi 3 is normalized to unity. We have thus constructed three kets, ket phi 1, ket phi 2, ket phi 3, which is orthonormalized. The inner product bra phi m ket phi n equal to Kronecker delta mn. This set has been derived from the set ket psi 1, ket psi 2, ket psi 3. That is not orthonormalized, that is inner product bra psi I ket psi j not equal to Kronecker delta ij. This process of construction of orthonormalized kets, ket phi 1, ket phi 2, ket phi 3, etc. from the kets ket psi 1, ket psi 2, ket psi 3, etc. is called Graham-Schmidt orthonormalization procedure. We have discussed the inner product of bra and ket, that is multiplying a bra with a ket. Can we multiply a ket with a bra? This we shall discuss in a future lecture.